great that we have a split the upstairs place, because we have also conference for the geography people. So this is only for today. This morning we still keep the part with the amphitheater where was opening. This one.
Good morning, my name is Scavuzzo and I am a PhD student at Polytechnic in Milan. Today I'm going to present to you a position paper that I've written, which is called a distributed file system of heterogeneous SaaS storage platforms. So the basic idea was born from the fact that, as you know, we have a lot of storage providers that actually give you some certain amount of space in the cloud to store your files. You have some free space, so you can store your files for free, but these plans may also have some limitations in terms of performance. So if you want to extend your storage space, or if you want to have better performance, then you need to pay for that. One of the problems that arises with these, with all of these plans is that when your space expires, you may have other files that you want to store, and so if you have limited storage space or limited performance, this may become really difficult to solve. And another problem is that all of us have different accounts, and so it's difficult to trace where we put our files and to reconstruct actually the path to retrieve them. A problem which is typically addressed to this storage is that of privacy and security guarantees, since these files are not encrypted and they are basically available to be read. And we all know about the leaks, the recent leaks that have happened with iCloud, for example. Another problem is that of installing a third-party client application in order to synchronize your data. And this may be a problem because you also duplicate your data inside your devices, and this wastes a lot of space because you duplicate the data both locally and remotely. To try to solve some of these problems, there are several clouds and several commercial solutions which actually try to aggregate this storage that you have. In that, they provide a unified view of the supported storage providers that you have, and they try to address just the problems of actually indexing your files, but they do not address the privacy issues, with the exception of OnCloud, which actually allows you to encrypt your data, but it is very slow and the overhead on the CPU is really considerable. Another problem is that they do not improve the performance of each storage that you have, since they cannot increase the bandwidth that you have on each storage provider. And finally, they do not exploit well all the space that is available in each of your storage provider. Let's see an example about that. So let's say that you have two different cloud storage provider accounts, and you have 50 megabytes of space left on each of these storage providers. And let's say, for example, that you have a file which is 70 megabytes large, and you want to store this file in this storage that you have. Of course, you have enough space, but you cannot store it because, you have just 50 megabytes free in each storage provider. So there are a couple of trivial solutions, which are basically buying additional space and store your file, or subscribe to a new provider and put your file. But then the problem is that you fragment your data over all of these providers, and it is difficult to actually going back and reconstruct them and download them. Another solution may be that of reallocating your files, actually shifting your files from one provider to another, but this solution may be too tricky and too difficult for the average user. Another solution may be that of zipping your files, splitting it, and uploading on the different cloud providers. But again, this is too tricky for the average user and too complicated and creates a lot of overhead. So the idea that I propose is that of automatically split the file into different blocks and dynamically place these blocks in different cloud storage providers according to the space that's left on each storage provider. So basically we need to keep track of the blocks that we store in the different providers. The system needs to be transparent from the user point of view, and should be agnostic with respect to the storage provider that we are going to use. Furthermore, we need to use a uniform naming convention independently from the storage provider, and it would be nice to have some sort of metadata associated with the files in order to have directories or access control lists and stuff like that. So the basic requirements are that it should be possible to use this system as a file system. So we would like to have the common operation like write, read, update, delete, and so on. It would be nice to have this system mounted in your computer as an external file system, so that you don't need to install a third-party application. And of course, we should have some kind of API to interact with it, and maybe build a web application to share our files with friends or other users. So the idea and the requirements that we have seen naturally led to the choice of adopting HDFS, which is the Hadoop Distributed File System, which is block storage. And we'll analyze briefly how it works, and now we're going to exploit it in order to realize our idea. So the basic architecture of HDFS is the name node, the master server architecture. We have the master, which is called a name node, and the slave, which are called actually data nodes. The data nodes stores the blocks and actually are capable of replicating these blocks across themselves, and actually manage these blocks and store them in the attached volumes. Whereas the name node keeps track of each blocks and communicate with the client applications, telling where the client actually should retrieve these blocks. The system is scalable, since the client application contacts just for the first time the name node and then each data node. So we can contact the different replicas of the data node separately, and the system may scale. A problem before version 2.0 of HDFS was that of basically the name node stores all the blocks in the RAM. So when we have billions of files, it may be a problem. So there's a system which is called federation, which works according to an active-passive pattern, which synchronizes two name nodes among themselves, and actually permits to have a system that is also fault-tolerant. And we can also have different name nodes which actually split the namespace that they handle in order to have more space and store billions of files in the RAM. So in order to read a file, for example, a client application contacts the name node and asks for the blocks that compose a file. The name node responds with a list of the blocks and the location of the data nodes. And then the client application simply asks each data node, according to a proximity factor, the proper blocks to recompose the files. And so you can see that the system is scalable. In order to write a file, the client application asks the name node to allocate some sort of space, and then it writes the blocks directly in the data nodes and communicates to the name node where it stored the different blocks. And you may see in the image that the data nodes are capable of replicating each block across themselves. So there are a couple of new features that we want to exploit from HDFS. One of that is the coordinated data node caching, which means that from version 2.3 of Hadoop, client application can request caching. The name node so coordinates with every data node to pin some blocks of each data node in memory, so that we can have enhanced read performance. And we are going to exploit this feature actually to achieve better performance. Other two cool features that HDFS implements are the networking file system gateway, which actually provides the network file and the networking file system access to HDFS, which allows us to mount HDFS as an external file system without the need to install third-party applications or libraries. And another add-on is that of Web HDFS, which actually provides REST APIs on top of HDFS, and it will allow us to build a web application in order to manage the different storages that we are going to attach to HDFS. So before May 2014, so before version 2.4.0, HDFS supported just one type of data storage per data node. This means that a data node was seen as a single storage unit, and the main node and the clients were not aware of the type of storages that were attached to the data node. Instead, after version 2.4.0, actually from version 2.4.0, the data node can attach different volumes of different types. We can have rotational disks, SSDs, and the data node can now store files on different types of storage and communicates by means of workbits to the main node the report of each storage. The main node and the client application can then specify which data node and which storage type should contain each file, each block actually of the file, composing the file. So now that we have finished the recap on HDFS and its new feature, this is the architecture that I'm proposing to build this new file system on top of the different SaaS storage platforms. Thanks to the heterogeneous storage that we were seeing before, we can use the data node